Hello everyone, my name is Jacoby Bussey and I'm a TA for Econ 210, and today we'll be going over question number 2 for the midterm, which has to do with research productivity. Okay, so first off, we're given a Romer model, so now this has production function t plus 1, this is minus AT is equal to BSLT AT beta, right? And that's very important. There's a difference between B and beta here. Okay, where B is said to be greater than 0, but it's also a constant. Okay, so everything else with the model is exactly the same as in class. Okay, that's good. That means we can use everything else we learned about the Romer model, except now we've just changed this one small aspect of how ideas are developed. So to write the fundamental equation of the Romer model, in this case, that is find an expression for GAT plus 1 only in terms of GAT and the model parameters. Okay, so how do we go about doing that? So first, key thing to remember is that the equation for the growth rate of technology, rather the growth rate of ideas, technology is equal to AT plus 1 minus AT divided by AT. Okay? And so, basically one of the things to keep in mind is whenever we do the growth rate, we're trying to figure out, okay, what's the growth rate in like time-wise? So for example, in this case, it's T plus 1. All we have to do is just say, okay, we take the variable, have it T plus 1 in this case, right? So whatever variable you have here, right? If it was T, you make this T, and then you subtract T for each of these, right? Subtract 1 for each of these. For this case, it's T plus 1, and then we're looking at one period before that, right? So you have just your T's. Well, if it was growth rate of T, then it would just be AT minus 1, AT minus 1. Just to let you guys know that just in case you guys need clarification. Okay, so we're already given the equation for AT plus 1 minus AT right here on the top. So we can just use that. So now we have BS LT AT raised to the beta, right? So AT plus 1 minus AT. Now we want to just maybe divide both sides by AT because this is the equation right here. And now we have BS LT AT. And so now look, we have AT raised to the beta minus, or rather AT raised to the beta, and we have a AT in the denominator, so now we can just do this, beta minus 1, because this is technically the same thing as BSLT AT beta times AT raised to the negative 1, and you add these together, right? So that's plus minus 1. Just want to showcase that, just in case folks were confused about how that was derived in the Romer model. In any case, now we have this equation for our growth rate of T plus 1. And this is great and all, right? We have this, but remember, we're trying to get the growth rate of A T plus 1 in terms of the model parameters and G, the growth rate of A at T, right? So we're not done here. We have a couple more steps we need to do. And so what we want to do is we want to see if we can find a way to turn this piece into GA, into the growth rate at T born. Okay, so how do we go about doing that? So the way we calculate it as far as the and we're deriving the Romer model is we start out with this, right? We know that 1 is the same thing as GAT divided by GAT, right? The growth rate at T divided by the growth rate at T, right? So these just cancel each other out, so we 1. So technically, we can multiply both sides by 1 and it wouldn't make a difference, right? So we could say 1 times the growth rate of A T plus 1 is equal to, parentheses, 1 times BS LT AT beta, right, minus 1. And then from here, we could just say, okay, well, we can replace this with the growth rate of A, T, right? And we could divide everything by the growth rate of AT. And so you might be thinking, okay, why would we add more variables to our function? Well, think about it, right? It gives us one step closer to giving us GAT on both sides, because now we have GAT on one side, we have GAT on the right side now too, but we need to get rid of this bottom one, right? And so if we want to figure out what's GAT equal to, right, it's best to figure out, well, if we want to get rid of this GAT on the bottom, what we're going to need to do is we're going to need to actually turn this into its more of its kind of its base form, similar to where we did with this. So think about it. If the growth rate of t plus 1 is equal to BSLT AT raised to the beta, right, minus 1, well, what would the growth rate of t be? Well, it would follow this same convention, right? It should probably have the same variables here, because t is just any random numbers, any random time, right? So if we're looking backwards in time, we're looking one step backwards, we should be able to just plug that into this equation and see what that is. So let's see. So if we wanted to find GAT, all we would need to do is just subtract 1 from each of the t's here. Why can we do that? Well, we just subtracted 1 from this t right here. And so if we're doing that, then we can subtract 1 from all these t's over there. And so from here, and another way to think about it is just, if we're trying to find the growth rate for a certain time, t plus 1, we look back and we say, okay, what's the labor population, and then what is our technology at the original time before that one? Well, we do the exact same calculations for this time for the growth rate of t. So it's going to be the exact same thing, except we're looking one step backwards at t minus 1 as opposed to t. Okay, well, how does that help us? Well, luckily, if we take our function here, not function, but rather our equation that we've just derived, we can copy this. If this is true, well, we can just substitute our equation for GAT that we found right here in for this GAT, right? So what does this give us? So GAT, t plus 1, is equal to the growth rate of technology at t times BSLTAT, beta minus 1, divided by BSLT minus 1, AT minus 1 raised to the beta minus 1. Okay, let's try to simplify this. So notice we have a B and an S on the top. So now we can just get rid of those. So we have LT, AT, beta minus 1, LT, AT minus 1, beta minus 1. And so, and don't forget, we also have this GAT here. Let's move it on the side. Okay. 2 minus 1. Okay, so does this look familiar to us? Right? Is there a way we can figure out what these values are? Well, yes, right? Because remember, we presumed that everything else from the solo model is the exact same. Well, if everything from the solo model is the exact same, that also means we can use this equation, that LT is equal to 1 plus n LT plus 1. Okay, that's great. But what if we're interested in this case, we're interested in LT minus one, right? How do we work that? Well, it's the same thing. It's just this is a constant factor, right? Constant factor rather. It's a constant, it's growing at this constant rate. So it's always gonna be growing at the same rate. And more importantly, if we just subtract one on all of our t's here, right? So we have LT minus one is equal to one plus n. Oh, my apologies. I actually wrote that incorrectly. This is, that would make any sense. This is LT plus one is equal to one plus n LT, right? Because we're saying that we have a population at time LT or time t that grows by one plus n, and now we have one plus n times that many people in that new time. Okay, so if we subtract one from each of these, now we have LT is equal to one plus n LT minus one. This is also true. So look at this. Now this looks more familiar, right? Because what we could do is we could divide both sides by LT. So now we have 1 is equal to 1 plus n LT minus 1 divided by LT. Next, we could divide both sides by 1 plus n. And now look. Oh, wait, oops. Almost forgot. Yeah, we actually want to flip it the other way. There we go. We can just divide both sides LT minus 1 instead. Okay. So now we just have this LT minus 1 is equal to 1 plus n. So we can replace this expression with 1 plus n. What about this one? Right? Okay, do you remember what we were talking about earlier when we were saying that GAT is just equal to AT minus AT minus 1 divided by AT minus 1? Well, we can use that information here, right? Because we have AT minus 1 here. If we could potentially manipulate this equation, then we could actually find a way to just incorporate another growth rate of AT into this equation. We could replace this value right here, this AT divided by AT minus 1 with something. See what we can do. So first off, we could divide both, we could just kind of break this up. So now we have AT minus 1 divided by AT minus 1, AT minus 1. That's the first step. Next, we can say, well, this is just 1, right? And so now, look, this is the same thing that we have up here. Let's leave that unchanged, right? So we have this. If we add 1 to both sides, now we have the growth rate of A times T plus 1 is equal to AT minus 1. Okay, look, that's the same thing as this, so we can replace this term with that. So let's just combine it all together. So we have, remember we found that LT divided by LT minus 1 is just 1 plus n. So 1 plus n times, we found that AT divided by AT plus minus 1 is just the growth rate of AT plus 1, right? And this is raised to the beta minus 1. Right? Times GAT. So look, everything is in terms of the model parameters, and I mean, or is everything's in terms of the model parameters, or it is in terms of GAT, which is exactly what we want as far as a fundamental equation. Okay, and also take note when we're thinking about our original Romer model. It looks like our little thing that we added, that B, didn't really do anything to our fundamental equation at all, right? So Makes it a little bit easier on us when we're doing the rest of the math that we don't really have to think about anything too different. It's just a matter of just making sure we get all the steps right. Okay, so question B is asking from an empirical perspective, does it make sense to assume that B, or rather beta, is greater than or equal to 1? Explain why not. So we learned about this in class, right? But I wanted to kind of want to dig into that by kind of going a little bit deep into the explanation of why that can't be. So you wouldn't have had to do this on the exam, but just for for the intuition for why we were not allowed to do that. It was already explained in class too, but just as a recap, we could derive this theoretically and understand why. So first off, empirically, when we look at growth rates of countries, right? Remember what we saw for the United States. We expected kind of a constant growth rate, increasing. Maybe you have like these little blips, expansions, but it's ultimately going at like a constant rate. What we don't expect to see is something like this, an exponential growth rate. So if our model, our theoretical model, predicted an exponential growth rate, we would have a problem, right? So in order to make sure the confines of our model remain aligned with the data itself, right, what we believe about countries that they should grow at these constant rates, then we need to make sure that the constraints of our variables align with that data, okay? And we can get a better intuition for what we're supposed to do. What does that mean for our case by deriving the growth rate of y? Again, you would not have to do this on the exam. You could just think of this as practice for understanding why this was, but it would have been fine just to talk about um, just that final equation that I'm going to show you. So this is, so the growth rate of, let me just do this real fast. Okay, so we're thinking about the growth rate of output per capita, right? And this is yt plus 1 minus yt divided by yt. Because remember, why we're interested in that? Because we're only interested in the growth rate of output, right? We see that the growth rate of output is not exponential. It grows at this constant rate. So this is equal to the growth rate of y, not a, t plus 1, right? We want to find this term. How do we find this? Well, what is our y for the Romer model? For y, it's just equal to a t k, and we presume that k was constant, very important. 1 minus s, lt, 1 minus a. Okay, so we have it in non-per capita terms, but we want this in per capita terms. Let's divide everything by lt, right? And so from here, now we have small yt, output per capita, is equal to a t k to alpha. And now what we can do is we can distribute this 1 minus a to both of these terms. So now we have 1 minus a, 1 minus s, 1 minus a, lt, 1 minus a, right? Okay. So now what can we do? Well, notice we have an lt in the numerator, we have lt in the denominator. We can subtract 1 from this LT's exponent to get minus a, right? And just make sure this is because this is technically the same thing. Well, just for this expression, it's technically the same thing as saying LT 1 minus a times LT minus 1, right? And if you add these together, that's just LT minus a. Just want to make sure that's understood as far as the math goes. We use that a lot, so very important to have that understanding. So now we have AT, capital, 1 minus S, 1 over A, and now we have LT raised to the minus 1. Okay, but this is technically the same thing as AT, KA, 1 minus S, minus A, divided by LT to the A. Well, does this look familiar to us? Well, that's just capital per capita, right? Because capital isn't changing, but labor is changing. So our formula for capital per capita is still the same. It's still capital divided by labor. It's still, and it's fine that capital is constant. It's just constant. We will use this fact later. So KT, K divided by LT. And notice they're both being raised by the same exponent. So we can just put them on the outside there. 1 minus S, 1 minus A. And look, now this is just capital per capita raised to the A. And notice this turned into, we actually have a time signature on capital per capita now because capital per capita changes, even though capital is not changing because the amount of people in the economy is changing over time. Okay, so now we have our formula for YT, right? Well, this is great, but we don't have our formula for the growth rate of YT. So how do we get that? Well, look, let's use the same method we used last time to derive that. So first off, we have the growth rate of, okay, YT. So if we want to find YT plus 1, we can just add 1 to T. So let's just do that. So we have a, let me just rewrite it down to make sure everything's there. So YT plus 1 minus YT divided by YT is equal to, might have room if I do like that. So is equal to AT plus 1. This is equal to capital per capita plus 1 is the A, 1 minus S, 1 minus A, right? Minus, and remember, so I added 1 there because we're looking at YT plus 1, but now since we're looking at YT, you want it in the same way we have it up there. So let me just bring this down actually. T, KTA, 1 minus S, 1 minus A. AT, KT, A, 1 minus S. Okay. The first thing we can note is that we could we could break this up. So now we have the growth rate of YT plus 1 is just equal to AT plus 1, KT plus 1, raised to the A, 1 minus S, minus A, all divided by AT, KTA, 1 minus S, minus A, minus 1, right? Because if you broke it up, then we just have this on the right side and it's on the denominator, so it's just 1. Okay. But now look, we know what this is, right? That's just the growth rate of technology plus 1. But what is this term? And these just cancel, right? Because that's 1 minus S. So this is the growth rate of technology, T plus 1, right? That's that term. And now let's figure out what this capital per capita growth rate is. Okay, so let's remember what the formula for capital per capita is here. So that's big K divided by N. This is, well, rather, we could also N or labor, either way. Right? So this is labor T plus 1 divided by K. Yeah, okay, just for consistency. So this is LT, right? So this is, yeah, this is growth rate at time T, and this is the growth rate at my apologies. This is LT, this is at time t, labor at time t, and this is labor at time t plus 1. So this is being raised to the A. Okay. So now let's figure out what this is. So now we have K divided by LT plus 1 divided by big K LT. Well, this is just the same thing as K divided by, right? And so we have this in the numerator of our denominator, of our total denominator. So we can just bring this right here. And this is in the denominator of our total denominator. So we can bring this up. LT plus 1, right? So these two K's cancel. Now we're just equal. Now we just have LT plus 1. Okay, so what's this? Well, we do our equation again. So we have LT plus 1 is equal to 1 plus n LT. Well, we divide both sides by LT. Now we have rather LT plus 1. Divide both sides by 1 plus n. Now we have this. We can plug this into our equation for this. So 1 over. So if we bring this and put it over here, now we have the growth rate. We have the growth rate of A t plus 1 is equal to I'm sorry, make this a little cleaner. Okay, the growth rate of y t plus 1 is equal to the growth rate of A t plus 1 all over this 1 plus n raised to the a. And this is because this is technically the same thing. So this is equal to 1 plus n raised entirely to the a. So this is the same thing as just 1 over 1 plus n. So just make it cleaner and make it look like that. That's the same thing. Okay? So we found this. So why is that important? Right? Why did I go through all that work? Oh, and my apologies, I forgot. Oh yeah, wait, oops. Don't forget our minus 1 over here. So why did I go through all that work? What was the point of that? Well, the point is, look at what we have as a variable in our equation for the growth rate of y, of output. GAT plus 1. Okay. Remember, we have the equation for GAT plus 1 right here, right? So we know that the growth rate of output depends on the growth rate of technology, okay? And it's positive, right? So it's in the numerator. So that means if growth rate goes up positively, that means if growth rate goes up in a fashion, then that means outputs also go up in that same fashion. So let's look at our equation for the fundamental equation again. So let's say that beta was greater than 1, right? Let's just say that it was some astronomical number. Well, if beta is greater than 1, right? If we distributed, okay, so yes, if beta was massively greater than 1, then this entire function will be exponential, right? Why is that? Because think about it. Let's say that beta was 3, right? Well, in that case, we would have GAT. Let me just copy this, make it a little clearer. So let's say that beta was equal to something like 3. Well, if that's the case, then we would have GAT plus 1. 3 minus 1, GAT 1 plus n, right? So now this is just GAT plus 1 squared, GAT. So notice, you don't even have to do the distribution. You don't even have to do the distribution of this squared term here to recognize that the highest term, I guess the highest degree of the term, when we distribute all this out would be GAT squared, right? If you did the full distribution, you would just find that GAT is the max, the highest exponent of that thing, right? Why is that important? So there's GAT plus a bunch of other stuff, right? We don't really care about that. What we do care about is that if we multiply GAT by this term, right, then it would just be GAT to the third. So that means GAT plus 1 is growing like this, right, to the right of, as GAT increases, this is growing like this. Same thing if we made, I chose B to be 3, but same story if it was 2, right? If it was 2, then the highest degree term for that would be, so we'd have GAT plus 1, right? So this is 2 minus 1. There's a GAT plus 1. Multiply that by GAT, and now you have GAT squared, right? Plus GAT. So now, again, this is exponential. It's growing like this. So why is that important, right? Why does that even matter? Well, here's the thing. If it's greater than or equal to 1, that means it's growing at a non-constant rate. Like it is growing in a fashion such that it will continuously get larger and larger and larger as it goes, right? But look at this. Look at our equation for output, right? If this is growing, let's say exponentially like this, well, that means that this is certainly going to grow exponentially too, right? Because it's in the numerator. But wait, we just said that in the data itself, we can't see evidence of it growing exponentially. We see it growing at a constant rate. So it can't be growing and continuously growing at a rate that increases. It has to be growing at a rate that's the same. But if it's equal to 1 or greater, it's going to be growing at a rate that is increasing. So we have a problem, right? So why can't beta be greater than or equal to 1? Well, because if beta is greater than or equal to 1, then output would not be approximately constant, right? We would be growing at a constant rate. It would be increasing. And that's a problem. We would see an increasing growth in output, right? Because remember, even in that linear sense, right, it's still growing, right? It's still increasing at this linear function. It's supposed to be constant. So we would have a problem. Okay. So remember, we want to see the growth rate be flat if we can. We want to see that growth rate growing at a constant rate. Okay. So now we're going to go to C. Assuming beta is less than 1, which is kind of giving good hope to the fact that we've done this correctly. Draw the phase diagram of the Romer model. Find expression for the steady state growth of technology in terms of model parameters. Does this depend on B, not beta? Explain why or why not. Okay, so let's copy this. Let's fix this. Okay. This is our fundamental equation. And so we know if we draw our phase diagram here, GAT, this is GAT plus 1. This is our 45-degree line. What is this function going to look like? Well, remember, beta is less than 1. If beta is less than 1. So if beta is less than 1, right? Well, that means that this term, the exponent for this GAT term must also be less than 1, right? Because look, if beta is less than 1, that means this term is going to be negative, right? If this term is going to be negative, so beta minus 1, right? And in fact, what we could do, so if we say that beta is smaller than 1, if we subtract 1 from both sides, we can prove that this will also be negative. That means this will be negative. So if this is negative, and this is being raised to the 1, that means we know that the term with the highest exponent must also be smaller than 1, which is going to give us a function that looks like this. Don't have to go that deep with it, but I just want to explain why the function looks like this, right? Because if this is negative, or this is a negative term, this is a positive term, and if we're adding those terms together because we're multiplying them, right? Negative plus a positive, that has to be, it has to be by its very definition smaller than 1 because you're adding a negative and a positive term, and the positive term is just 1. So it has to be smaller than 1. So it has to be this shape. So in any case, it seems that we have a steady state. Steady state because we have hit the 45-degree line. This is GA star. Okay, and this is the equation for this line right here. That allows space to write it. Beta minus 1, GAT. Okay, so well, this is great. What is the steady state? How do we know what that steady state term is? Well, just like last time, remember in the solo model, when everyone figure out if we have a steady state, we kind of remember what it means to be a steady state. We are at a steady state when a term at t plus 1, in this case the growth rate, is equal to the growth rate at time t. That just means that I have not moved, right? If the growth rate at t plus 1 is different than the growth rate at t, that means I've shifted somewhere, I've moved. But we're at a steady state, we're not moving anymore. Our economy is sticking to a certain level, right? This has to be true if we're at a steady state. Well, if this is true, well, that implies that GAT plus 1 minus GAT equal to 0 must be true. Okay. Well, if that's true, and we have our equation for GAT plus 1 right here, but that means all we have to do is just plug in our equation for GAT minus 1 into this, and then from there, subtract that by minus GAT, and then solve for the steady state. Let's give that a shot. So we have our equation. Let's see if it's still copied. Yeah. Okay. So GAT plus 1, we have 1 plus N GAT plus 1 beta minus 1 GAT. And know that these are technically stars, right? Because we're at this final joint, but I want to just keep it consistent so then you guys can understand what we're doing easier. Okay, that's equal to 0. Okay, so what's the first step? So first off, we could add GAT to both sides, right? Beta minus 1 GAT is equal to GAT. So look at this. Well, we can just divide both sides by GAT, right? If we do that, then in that case, we then get 1 plus N GAT plus 1 beta minus 1 is equal to 1. Okay. Well, now we can divide both sides by 1 plus N. And then finally, what we can do there is GAT plus 1. We can raise both sides to the beta minus 1. Or rather 1 over beta minus 1. Okay. Now we can add 1 to both sides. rather subtract 1, my apologies. Now look, this is the equation. So this is right. So this is not G at T, right? This is G A star. This is the steady state. This is the equation. But we can make it look a little cleaner, can't we? Because look, we have something in the denominator here we know is going to be negative. It's always cleaner if you know the numerous should be negative to kind of make it positive looking. So you have to think about things flipped. So in order to do that, what we can do is we can utilize a little trick here. So 1 is equal to -1 times -1, right? Well, that's true. Then we can just multiply 1. We can just do this, right? That will tell us be the same thing. So if that's true, then we can do is we can put this -1 over here and then put this -1 over here. That will also be the same thing. So we could just, when we raise something to the -1, we flip it. So we have 1 plus n over 1, which is the same thing as just 1 plus n, right? So we said 1 plus n. And this is now being raised to the, we've multiplied both sides by, we multiply this by -1. So that means we have 1 over 1 minus b, beta, -1. And there you go. This is a lot cleaner way of doing it, but it's the exact same thing, right? Exact same things what we had up above. Okay, so now the question also asks, right? Does this depend on B? Not technology, not beta, right? That's a completely different thing, B. And so look, do you see B in this equation here? Well, no. So if B is in the equation, isn't in the equation for the steady state, then ultimately, in the long run, B does not matter in turn for the growth rate, the steady state growth rate of technology, right? And so similar to how in class we found that it doesn't actually depend on S, it also doesn't depend on this B either because it just divides out way earlier before we even calculate the growth rate calculation. Rather, as we're calculating the growth rate calculation, it just divides out. Okay, so beta is important to it, right? Because beta is in the equation, but B is not. B is on the equation, so B is not important. Okay. So now we're going to ask a new question here. So D, suppose that starting from the steady state, researchers in the economy suddenly become less productive, is captured by permanent reduction in B, right? So now we're producing less ideas than we used to at yeah, we're not less productive yet, fine. What is the effect of this change on the growth rate of technology in the short run and in the long run? Explain in words and show with arrows in the phase diagram. So let's see if I can copy my phase diagram here. Go. Okay, straighten this out. We're now asking what happens if we reduce B, not beta, right? Not beta, B. So if we reduce B, do any of these lines shift? Do we see any shift in the equations, in the equation right here? Well, no. Why not? Well, because there's no B inside this equation, right? If B was in this equation, then we might see a shift, but there's no B here. So if there's no B, then there's no shift in the equation. So does anything change? Yes, and this is why it's always important to write down the equations associated with a changing variable, right? And so in this case, it's certainly a variable of interest, right? So we know what the formula for GA is, right? GAT. If we go back up, Or if you remember, growth for GAT, the growth rate of technology is just this, beta minus 1. Okay, wait. The growth rate of technology at time t has b as a part of its equation. If this goes down, this has to go down immediately, right? Because, so if it started up here, and if b goes down at time t0, this has to shoot down. It has to immediately, because b has gone down, right? But what happens next? Well, let's look at our model to see. And so first, let's put that down, right? Let's show that b has brought this down. So now, look, we're jumping here. And at t0, we are now at this point, right? At time t0 plus 1, we are at this point. Because this has just happened. We are now at this point right here. Okay. So what happens next? We just drop down. What happens next? Well, look, this line, right, our line for our equation is above the normal line. The normal equation line is above the 45-degree line. So that means we just keep going to right and up like this. And now look. So initially, we get hit with the bump. We go all the way down here. And then look, we're going all the way right back to where we were, to our original growth rate, to our original steady state. So wait, it seems that in the long run, it doesn't have an effect, but in the short run, it does have an effect. It falls. And we could have actually, we already knew this just by looking at the growth rate equation, the steady state for the growth rate of technology. Because look, the steady state for the growth rate of technology right here is just 1 plus n raised to the 1 minus beta minus 1. There's no b there. So if that doesn't change, that means the steady state for technology doesn't change either. So that means in the short run, we see this, we see this decrease, we see it fall. Then in the long run, it eventually goes right back to where it was. The growth rate goes right back to where it was. And this is the phase diagram showing that. Okay. So next, we have E, right? We need to draw the time path for the natural log of technology, right? ln AT. The natural log output per person, L and YT, right? So it's a good thing we calculated what the equation for YT is, right? Before and after the change from part T. So let's see what happens. So first, we have T, right? So it's ln A, right? So this is growing at a certain constant rate, right? Because we're thinking about in terms of growth rates now. Okay, so it's growing at a certain rate. And we know what this rate is. It is growth rate GA star, right? Because where are we before time t0? We're at this steady state, right? We're at this steady state right here. So we know that's the same thing. Okay, now what? Well, something happens at time t0. We change technology, right? And look what happened in our phase diagram. We saw an instant jump, an instant drop, like this, right? An instant drop. So if we see the instant drop, that means we know that we get, by the way, it's an instant drop in the growth rate, right? In the growth rate. So if the growth rate drops, that means the slope, which is tied to the growth rate, also drops. It should go down. What does it look like when a slope goes down? If the slope is high, it's sharp, like this. If the slope is low, it is like this. So that means when we draw our slope, right, at time t0, it should go down like this, right? But then what happens? It should go back up, right? Because look at our graph here. we see that yes, it is going up back to the growth rate initially was, right? So the slope of that line right here is GA star, and then the slope should go back to this GA star at some point in the long run. Okay, so let's just kind of showcase this perpendicularity, the parallelism between the two things. We can kind of draw this line. GA star. You can go further here by just saying that this is also GA star. Okay. And so now we're asked the same question for ln yt, right? And so what happens to ln yt? Let's look at the equation for ln yt. Let's look at the equation for the growth rate of yt. Get it all the way back here, right? So notice the growth rate of yt does not have beta inside of it. I mean, not beta, it doesn't have b inside of it. So because b is not inside of this growth rate, we know for a fact that there's not going to be a jump in this equation, right? So there's no jump. We know that it's just changing based upon the growth rate of technology. So whatever happens to the growth rate of technology is also going to happen to the growth rate of output. Okay. We also know by the properties of steady state that if one of these terms is at a steady state, so for example, if GA, the growth rate of output, I mean the growth rate of technology is at a steady state, we also know that the growth rate of output must be at steady state too. So that means that the steady state's kind of, if you're at the steady state's kind of flow between terms, basically. What am I trying to get at? What I'm trying to get at is because of the way the equation is shaped out, there's no direct effect to the growth rate of y for this equation, and basically just follows exactly what happens to the growth rate of technology. So it's just going to look like this. So before this, we were at a certain growth rate of output, y star. And then GAT went down. So that means the growth rate of YT went down with the same level slope. And then it's going right back eventually, like that. So these are two perpendicular lines. Parallel lines. Okay. This time T0. Okay. Let's see. Is there anything else for that question? Explain your answers in words. Be sure to and we talked about that. The direct and indirect effects of the change. All right, and so that is the question regarding the Romer model for the midterm. Have a good one.